We are the very model of a CS intellectual. We've memorized the memory of variables receptacle. We know how to dereference, and those pointers, they are horrible. Addresses and segfaults in my code are quite improbable. Calculate all manner of equations mathematical. The cube root, the next primes and runtimes, most of them quadratical. We're very well acquainted with arrays just one-dimensional.
And the missing semicolon, I assure you, is quite intentional.
I assure you is intentional. His missing semicolon, I assure you is intentional. His missing semicolon, I assure you is intentional.
This week in FoA with just 2 lectures, what a shame it is. Yet C2D arrays will have your course of read from inities. In short, and matters virtual and runtimes are perpetual. We are the very model of a CS intellectual.
And that should begin FoA in a light-hearted way for your week with the mid-semester tests. Today, the first element of our lecture, as always, is a bit of a historical introduction to one of the figures relevant to the material for our week. In this case, it is Don Knuth, who is actually still alive today. He is the father of algorithmic analysis at age 84, also known as the professor of the art of computer programming, thanks to his creation of the tomes, the multiple tomes that you can see up here on screen, The Art of Computer Programming, and he has recently retired from his professorship at Stanford, as well as a stint in the National Security Agency as a codebreaker. Among his many inventions are the KMP algorithm that we may learn in class in the coming weeks, depending on if I can get my brain around it so you can get your brain around it. He also created TeX, which was the progenitor of LaTeX, a markup language that hopefully some of you have seen in your mathematics or computer science classes. And on top of this all, he is also a Turing Award winner. One interesting fact about him is he's very proud of his connection to China and the Chinese people. In fact, one time when he visited Tsinghua University, Francis Yao, who is a very prominent computer science professor, married to another prominent computer science professor, gave him the name Gao Dena, a Chinese name for him to use in perpetuity. And in fact, if you visit his website today, you'll see his name in Roman characters as well as in Chinese characters. And he is very proud of this legacy and of his connection to China, as well as the translation of his tomes into Chinese for students and professionals there to learn. One interesting feature about his books are what are known as Knuth checks. If you can spot an error in one of his books, you can write to him with the error, and he will send you back a check for $2.56. Why $2.56? Of course, that's the size of a char. Knuth has sent out more than $20,000 worth of these checks, but of course you'd be a fool to cash them. Their value as memorabilia is worth far more than the actual face value on the check itself. Now we move to a continuation of last week's material before we get to the mid-semester test. Now again, to reassure you, this material will not be on the mid-semester test, only what we've covered until now. In this week, we're going to look at 2D arrays before moving on to analysis of algorithms, and in particular, search algorithms. 2D arrays are very, very similar to 1D arrays, which are very similar to pointers, which at the end of the day, it all just boils down to memory, different ways of referencing chunks of memory. However, C does not check array bounds or pointer bounds, so it's a trap. Unfortunately, if you access memory outside that of which you've been allocated, you get a, nice and loud, segfault. Exactly. So this can happen with 1D arrays, with 2D arrays, and with pointers. In fact, accessing arrays out of bounds or accessing memory out of bounds is one of the key ways that hackers and malicious individuals can actually gain access to your system and run their own code. I may do a little supplementary module on this for you to show you exactly how one can take a programming error and turn it into a way to take control of someone else's computer. One question that you might already have is how many bytes does a 2D array consume? We know that a 1D array is just a linear collection of memory addresses with one of the type allocated for each of the spaces in the memory. Knowing this, we can probably intuit how many bytes a 2D array consumes using similar principles. So who wants to give a stab at how many bytes this array might consume, remembering that the size of a char is 1 byte?
I think 8. I'm not sure though.
Yeah, why do you think 8?
Well, it would be 4 rows and 2 columns.
That's exactly right. So 2D arrays, despite their imposing appearance, can be thought of as just collections of 1D arrays. This is not C syntax, but as Claire pointed out to us, we can think of this as a collection of subvectors, which each in themselves are arrays. So we have 4 rows and 2 columns. Each of the columns have 2 in them. Because C's memory is in fact much more linear than our representation of it, instead of treating the array as a physical location with rows and columns, we can think of it as just a sequence of bytes going up and up and up. So once we've gone through the first row, if we go to the next memory address, we'll get to the next row. In this way, you can use pointers to access all the elements of a 2D array as well, just by using our standard pointer arithmetic. If I want to access an element of a 2D array, the syntax is fairly intuitive. One simply uses the normal array accessing syntax, but appends to it another pair of square braces, and within that puts the relevant index. So we have row column A11 equals D. That gets me that element over there in row 1 and column 1. But one key thing that might get you a little confused is that just because the array is 2-dimensional doesn't mean that it's a pointer to a pointer. Because a pointer to a pointer points to something that points to memory. And really, a 2D array is just a pointer to a chunk of memory, but the way we're talking about the memory is a little different. So because a 2D array is really just a linear set of elements in memory, we would still use a single pointer to reference the entire collection of addresses. So in our first demo, we have two-dimensional array initialization syntax. We are going to declare 2 different arrays, one A, one B. Both of them will have 4 elements, but we'll use 2 different forms of syntax to create them. In the first one, we will specify only the second dimension of the array and just leave the compiler to figure out the rest. In the second syntax, we're not initializing it, we're only allocating the memory for it, telling the compiler to set aside the memory. But in this case, we have to give it both dimensions because the compiler can't automatically figure out the size of the other dimension based on the elements we're giving it. The reason for the peculiarities around C syntax of 2-dimensional arrays is fairly arcane. So unfortunately, you just have to learn the set of rules around what's permissible and impermissible until you gain more sophistication and the ability to read a bit more into why C was constructed the way it was. We also have a third syntax, one moment. We also have a third syntax that we can use to create 2-dimensional arrays in C, and this is represented by our array C. We still have our 4 elements, but this time we actually represent it as the 2 sets of rows. So we'll run this, and it will create those variables. And now I have a function in which I'm going to try and use my first array A. Will this work or will this not work, and why? Liam, my taped microphone pair. Emily, you have the misfortune of attending live today, so you're getting picked on.
Yeah.
Yep. Will that line over there that's highlighted, will it work?
No.
Say a bit louder.
No.
And why don't you think it'll work?
Because it's not a pointer to a pointer.
Exactly. Emily's got it exactly right. Remember that 2D arrays don't decay to pointers to pointers don't decay to 2D arrays because a pointer is just a reference to a chunk of memory, and a 2D array is itself just a reference to a chunk of memory. It's not a reference to a chunk of memory. So if we give this a run, we'll probably get a big complaint. Yep. Cannot initialize objects, mismatch between the functions, no matching function, candidate function is not viable. The next one, however, should work. In this, notice that we didn't actually give the function both dimensions of the array that it's expecting. We've only given it one dimension, just like the initialization syntax that we used up earlier. Write down, if you have a pen and paper handy, what you think the outcome of this line of execution will be. And I'll scroll back up for a second so you can see the declaration of A. So there we have what A is. And I'll scroll back down again. So let's give it a run and see if your guesses are correct. Here we have another example of a way to access the same array element, only this time we have given in the function prototype, we've actually given it both indices. So we've told it ahead of time that there are going to be 4 elements. Now, there is probably a way of tricking the compiler into running this function, even if the value you're passing in doesn't contain exactly 4 elements. The code will run and will execute as long as you typecast things properly so the compiler will allow it. However, these are workarounds and will make your code more dangerous and more susceptible to the kinds of bugs that would let hackers in and control your program. So highly advisable to be very careful with your types and your array indices. We'll give it a run, expect it to work, all good. We also have the normal methods that for single-dimensional arrays of accessing each of a 2-dimensional array's elements. So again, I'll give you a few seconds to write down what you think this code will do. It goes from 0 to 4 and accesses some array elements and prints them out. So write down on your pen or pad of paper what you think will be printed out. And I'll add a space after that %d. And for the zoomies, there you go, 1, 2, 3, 4. It is accessing the array elements in order by using the fact that every time we get to 2, we reset the row index back, we reset the column index back to 0 and move to the next row. So that's the same as operating modulo 2 or clockwork arithmetic 2, or the same thing as taking this modulo operator, the remainder operator that we have over there. Likewise, because I is an integer, we can do integer division on the value of I and get the row that we're up to, because any value such as like 1.5, the 0.5 is just going to get truncated, so it will give us the exact value of the row, and our array access will work correctly. The last demo, I'll give you only 10 seconds to figure out this time. The last code demo, you already know what A is. A contains 1, 2, 3, 4. Take a look at the code. And again, we get 1, 2, 3, 4. This time, we are explicitly using a row index and a column index to access the same elements that we did before. Now, you might ask, why would I use the confusing syntax, or why would I use the long syntax? This is just to give you different perspectives on the way that these arrays are actually represented, on the ways that you can access their elements. Which of these two you choose to use is a matter of code style, something that will become increasingly important for the rest of this course. It's a matter not only of taste, but of maintainability. So what will make your code easier for someone else to read, or easier for someone else to deal with later? So in some cases, it'll make more sense to have shorter code, and perhaps you'd add a comment explaining what it does. If you're working with experienced programmers, perhaps those programmers are used to seeing the shorter one-line version, and that'll be more intuitive. In other cases, you might want to be more explicit and give people more guidance as to what exactly you're doing, even at the expense of adding a few more lines to your code. And so that's why we have the second version as well. As we can see through all of our examples, n-dimensional arrays are treated as arrays of arrays by the compiler, and this includes when we pass them into a function. So when we have our syntax, you can think of the first chunk of the type declaration for a 2D array as referring to an array, and what is contained within the array is in fact more arrays. So it is an array of arrays. And that can be one helpful way to break down a complicated type definition, which is what we'll have in a minute when we create some more complicated types. So we've seen C's basic types. We've seen chars, we've seen ints, we've seen floats, we've seen doubles. But what if I want to make my own one so that I don't keep passing around arrays of arrays of arrays of arrays, or pointers to pointers to pointers to pointers? If I want to start mixing things together and give them names that are much more convenient, well, C lets us do this through something called a typedef. The way a typedef works is it creates a new type based on this line, this special declaration that you include within your program. To create a new typedef, prefix the line with the word typedef, then the type of that you are going to make a shorthand for. So if I want to create a new type name for long, if I want to call long, if I want to call it biggie boy number, then I would do typedef long biggie boy number. In this case, here's a bit of an exception because I want to create a typedef that maps to an array of longs and not just a long itself. So what I do is I do my typedef special keyword statement, the type of the thing, then the name of the typedef, so this would be just like biggie boy number, except at the end of it, I'm going to append the array syntax to indicate to the C compiler that the typedef should create a mapping from the type of long array 560 to the name student IDs underscore T. Now here, really important to remember, student IDs T is not a variable, it's a type. So if we want to declare a new variable, instead of saying long myvar 560, we could instead say student IDs T A, where A is the name of the variable that we're creating, and student IDs T is going to be the type. We'll see this in action in our next code demo, matrix add, where we will typedef an array type. Here we have two of our first typedefs in the course. We have a typedef for a double array, and we're going to call this double array type a vector. One way of thinking about this is to go to yourself, okay, what is a vector? A vector is a collection of numbers, and so I know that this line in the code is creating a new type. It's creating a vector type. I'm not calling this isn't a particular vector. It's telling C that we want to create a new type of object in the world, and these types of objects are going to be vectors. So I might make vectors A, B, and C, or I might make vectors that correspond to some kind of physics problem. But I'm going to let the compiler know that from now on there's a new type in the field, and this is the vector type. We then immediately after create a type using the type. So the next type of type we have is a square matrix, and a square matrix is just a vector of the same length of vector. So if we have a square matrix, it's an m by m matrix. And if we've said that vector is a double array of size m, then an array of vectors of size m is equivalent to an m by m array. In this case, we've defined size as the number 5. So this is going to be a 5 by 5 array, or 5 different copies of vectors of length 5. Boy, that's a bit of a mouthful. Let's look at our main function. Here we go. We're going to create 2 of these vectors, A and B, and a square matrix C. We're going to fill up our vectors with some values from 0 to 5. We're going to fill up our array A with half of the value that we are, half of the value of the array index I. And for our second array, we're going to calculate 1 on 1 plus the array index, and then print it out. Let's scroll a little further. We print out the array, print out the array. Then we're going to call 2 different add functions. Vector add over here that'll add 2 vectors together. We're going to try and add 2 square matrices together, so we'll have a function to add matrices, and then we're done with our main function. For our first square matrix adding function, we are going to just add the 2 vectors together by their indices. So remember, to add 2 matrices together, you find the identical index in each of the matrices and store the identical index in the result. So the value of Aij plus the value of Bij, which is the same index in both of the matrices, add them together, that'll be your result in matrix C. And that's exactly what we're doing here. We're looping through every single value in the matrix and then adding them together and storing the result in our new matrix. Notice how, thanks to our type defs, at the top of our function, we didn't actually need to add this nasty array syntax in there, specifying, well, maybe one of the rows or one of the columns, or specifying both of them. Instead, we could use our newly type defed square matrix that will take care of all the details from us. We also have a function to add vectors. Adding vectors is similar to our 2D square matrix addition. You add the same index in both of them. So we loop through the size of the vector. Our vectors are of size n, which was passed in as an argument to this function because we need to know how large our vectors are. And for each of those indices, we simply add the two indices in each vector. We add what is at that index in each of those vectors together to produce the output 1. Square matrix add 2. And this is where you see that we can actually compose our vector add function from earlier to produce the same outcome as we did using our nested for loop. Because we know that addition in matrices is equivalent to just adding the vectors individually, we can do this process as well, looping through each of the n vectors that we know that this will work because it's a square matrix, and then just adding those vectors together. So I had a student question on this slide, which is there anything left to discover in algorithms? Why are we spending so long learning about how to make these things if we already know the best way to say sort an array? I just told you what the algorithms were. I told you, bubble sort's this good, insertion sort's this good. Is there anything actually new fundamental to learn? Well, let's take matrix multiplication. This is very similar to the stuff we were just doing, only instead of adding two matrices together, we want to multiply them. This is an article that came out, I can't see the date quite at this resolution. Might have been, 2021, there we go. About a new discovery in matrix multiplication, getting closer and closer to an optimal time algorithm for matrix multiplication. However, we don't yet know what is the fastest that one could possibly multiply two matrices. We can come up with a pretty naive method, which is to do the way that you'd multiply matrices by hand, which it turns out is an n-cubed algorithm. Can we do any better than n-cubed? It might surprise you to learn that the answer is actually yes. The fancy 2020 algorithm that was written about last year, in fact, is big O of 2 to the 2.3 instead of n to the 2.3. It is considerably faster than an n-cubed algorithm. Imagine you're plotting a cubic function versus a quadratic function, and then you plot a function that's somewhere in between those two. Because the growth of n cubed is much, much faster than n squared, when you're working with a real problem, the difference of lowering this even almost all the way to 2, but not quite, makes a really, really huge impact on kinds of problems that we really care about. Among these kinds of problems are creating the index for Google search. So when Google figures out what to recommend you when you do a search, they're doing matrix multiplication. When Netflix tries to figure out what to recommend you, they would traditionally use matrix multiplication. Now, some of these algorithms have varied a little, and so I can't tell you what Google's secret sauce is today and how much matrix multiplication they're actually doing, but it would be safe to say that this is a major, major problem for large organizations dealing with very large amounts of data and doing machine learning. If we can make matrix multiplication faster, we can solve a whole number of real problems much, much faster. But this jump from n cubed to n to the 2.3 certainly wasn't instant. It took quite a period of time to get all the way from our n cubed algorithm, which was known 1970 and well before probably. It took us all the way to 2020 to get our n to the 2.37 algorithm, or whatever it happened to be. But you can see that there was a fairly large jump between the n cubed algorithm and then the n to the 2.8 algorithm that was discovered in 1970-ish, down to about n to the 2.5 in 1985. And then ever since then, we've been making tiny, tiny, tiny improvements to the runtime of matrix multiplication. Now again, this might seem to you to be of very little relevance, but each one of those tiny, tiny gaps is worth millions and millions and millions, if not billions of dollars, not only to the person discovering it, but to the companies that then get to use this to make their problems that much faster. Will we ever get all the way down to an n squared algorithm? Well, that is left as a problem for your mid-semester test. I did warn you that it was going to be quite difficult, and so at the end, a full 10 out of 10 will be awarded to any student who successfully comes up with a n squared algorithm for matrix multiplication. If you finish early, which I'd a little skeptical about because it's a hard test, then feel free to sink your teeth into this problem. Just be aware that you're competing with 100 years of, at least, of mathematical advances. This leaves us back to where we started at the beginning. How can we ensure that our algorithms are efficient? How can we ensure that our algorithms are correct? And this is what we're going to be spending the rest of today on, and then tomorrow's lecture on, and then probably a good chunk of next week as well. So number one, for any algorithm that you write, it must be correct. Your algorithm is not going to be much use to people if when someone gives it input that is within your expected scope of input, it doesn't work. There is a caveat to this, in which there is a whole world of probabilistic algorithms. So these are algorithms that you say are likely within some bound to give you a correct answer. So you could say, for example, that every time you run the algorithm, it'll tell you with 80% correctness whether your number is prime or not. You might ask, why is this useful if I don't know if my algorithm is giving me the correct answer or not? Well, you might be able to run the same algorithm more than one time with the same input, and based on the randomness that's fed into the program, get a different answer. So if I ask it, is my number prime? It says no. It says, is my number prime? It says no. Is my number prime? It says no. And you keep doing this a few times, and after a while, you ask, is my number prime? And it says yes. Depending on the way you've constructed your algorithm, you might know that if it says yes, it's definitely the case that it's a prime number. And if it says no, it's only probabilistically not a prime number. So by running the same algorithm over and over again, you can get closer and closer. You can get more and more confident that the answer it's giving you is correct. And finally, in some instances, even with a probabilistic algorithm, you might have complete confidence that the answer it's given you is in fact correct. Your algorithm must also run within reasonable constraints. So depending on your exact scenario, if this is in a test or in a programming interview, your constraint will be big O time or maybe even big O memory. So how much time and memory does it use? But there are other constraints that exist in the world that are important as well, such as how much electricity will this use? How many different CPUs will I need to run this? And these are very important factors when not only choosing which algorithms to use in actual code, but when designing algorithms to use in actual code as well. In this class, we're not going to focus on the electricity costs and on parallel algorithms, so how many different computers you might need to make it efficient. We're going to look at the simple case of just programming power, processing power, and memory. Number three, and this is traditionally not part of algorithms classes, but I wanted to point out to you as well, is that certain algorithms take a lot more time and energy to get right. And depending on your scenario, you should think very carefully before implementing a very, very complex algorithm that'll cost you a lot more engineer time to write, a lot of engineer time to maintain and debug, if it turns out that the thing you're using it for doesn't actually require that much of an increase in efficiency. So you could get your n to the 2.37 matrix multiplication algorithm, but if you're only multiplying 3 by 3 matrices, that's probably overkill, and an n cubed algorithm would be appropriate. So balancing all of these different considerations is one of the things that will make you a better coder. This takes us to an example problem that this is one of my favorite problems in all of algorithms for its simplicity, but also for the way that it illustrates some of the key concepts. So in the dying minutes of the class, I want one volunteer to help me find a name in the white pages. Hopefully someone new. Backwards baseball cap in the red. Yeah, that's you. Come on down. Nawi, I think I've caught you once before. Okay, so here is a white pages, ordinary white pages. It's up to date, 2022, for the city of Melbourne. So take that, and I want you to find me someone whose last name begins with, let's say Cohen. I want you to find me a Cohen in the phone book. C-O-H-E-N. Let's just say you found the page. We're on Collie. That's close enough. So why don't you tell the class, hold the microphone pretty close to your mouth so everyone can hear you. What was the process you used to find a name in the phone book?
So what I did was to cut the book into half, and then I realized that C is before the middle, so I went backwards. And after that, until I reached the letter C, then I look at the second letter, which is C-O. Then if the word is after C-O, I'll go back, or if the word is before C-O, I will go forward. I don't think that's linear search, but...
That's not linear search. So why don't you give us an example of linear search? If I want to find the name Cohen in the phone book using linear search, can you, if you already know what it is, you want to give us a demo in the phone book?
For linear search?
Yeah, for linear search.
All right, so for linear search, what I would do is to basically just start from the start. And then
Go to the start. Start of the phone book, first page, and read out for me the names that the computer is going to look at. Let's say that here's the first page over here, and we're looking for Cohen. So,
all right, so the first name that I see is Aaron.
Is that Cohen?
It's not Cohen.
Okay, what's the next name?
The next name is Arsman.
Is that Cohen?
No.
What about the next one?
The next is RT.
Okay, so we can see that this is going to take us an awfully long time to, thank you very much, Nawi, appreciate it. Can we have a round of applause for Nawi? So we can see that it'll take an awfully long time if we're using linear search to find the name Cohen. We're going to go through every name in order. However, it's still going to be useful for us because we know if we start at the beginning and try and go every name until we hit the name we're looking for, it's probably going to be correct. And we'll find a way of formalizing that shortly. Fortunately for us, though, Nawi has also given us a sneak peek at another algorithm, and this one is called binary search. So what Nawi was suggesting was, let's say I'm looking for the name Cohen, and I open the phone book halfway in the middle, and this is at J. Well, C is earlier than J, so I guess we don't need that half. Cohen's going to be in this half. Now let's open it halfway again. We're at DE. Well, we don't need that. We don't need this half because Cohen's not going to be there. I guess we can throw out that half again. We repeat our process. Let's go halfway. Buckney. Is Cohen before or after Buckney? After. So what do? Can throw away this half. Okay, let's repeat, and shouldn't take us many more steps. Now I'm on Clift on this side and Coffer on this side. And at the bottom of this one is Coates, C-O-A. So which side am I going to take? The left side, this side, or that side? A or B? B. Okay? B. And we know based on how many different chunks I've thrown out how many times this is taking us. So let's go halfway again. I have C-O-R on that side and C-O-U on this side. A or B? Keep A. We're almost there. C-O-L or C-O-M, A or B? A. And we'll just stick to getting the right page. So now I have COF. Is this COF? No, COF to COL or COL to COL? A or B? A. And we've got the page with the koans. So instead of going through however many hundreds of thousands or tens of thousands of names are in the phone book, this took us 1, 2, 3, 4, 5, 6 steps. And this is an illustration of why algorithmic improvements are so important, because we allow the computer to just with a few comparisons get all the way to one name in the middle of our giant phone book. And that will be it for today. Thank you very much, and I'll see you tomorrow.